I was at the ASE conference and discussing the field inside a spherical shell. The question is, how do we know what the field is inside the Earth? How can we work out what the gravitational field is beneath the Earth's surface? Right, okay, so stage one, let's draw the Earth. Here's the Earth, it's green. Okay, here we are, there's the Earth, right, there's the Earth. And when we're outside the Earth, we're fine. We reckon that the field is, depending on the distance r from the centre, the gravitational field strength, little g, is equal to minus gm over r squared, where m's the total mass of the Earth. But what if we were beneath the Earth's surface? Okay, we're going to make a simplifying assumption. We're going to assume that the Earth is a sphere of constant density. And let's say that we've got the kind of radius of the Earth there, r, and we're there, so little r is smaller than big R. So what are we going to do? Well, we're going to imagine dividing the Earth into two pieces, the bit outside and the bit inside. So that's the bit that's inside, and the field due to that is what we are going to need to calculate. But first, we're going to need to think about the bit outside. So what about this bit here? Why do we not need to worry about this bit? Well, there is a reason for that, and the reason is as follows. Let's think of a hollow sphere like this. Say this sphere is completely hollow. It's got a mass, but it's got no thickness. There's nothing inside it. Now, if we think about being in the middle, right in the middle, it's clear that the gravitational effect of the sphere is going to cancel out. Every bit is going to be kind of pulling equally like that. And so you can say that the field in the middle is zero. That's fine. But what about if you weren't in the middle? What if you were somewhere else? What if you were like there? Okay, right. Now, this argument is something I saw in the Nuffield physics book from the 1970s. And what you can imagine is take a little small kind of angle here like that. There we go. And a little small angle like that. Okay. Right, sorry, not very good drawing, but you get the idea. Okay, right. Now let's say that this is in the ratio. That's obviously further away from that than it is like that. So let's say that's a ratio of 3 to 1 there. And then if we take this there, let's think of that little mass there. Well, it's 3 times closer to the point here, P, than this mass here, yeah? It's 3 times closer. So since it's proportional, g is proportional to 1 over r squared, exerts 9 times more kind of field strength. Let's call this stuff here kind of A, and let's call this stuff B, yeah? More field strength than B, since it is 3 times closer. But on the other hand, look, that thing there, because these triangles are similar, it's going to be 3 times less high, and also importantly 3 times less wide than B. So it is 9 times less massive. That's the business end. So therefore, the gravitational field due to A is the same size, but in opposite direction to that of B and cancels out. And importantly, for every direction, there are going to be corresponding areas on opposite sides of the sphere that are going to cancel out for P. And therefore, wherever P is, you're going to get absolutely zero field due to A and B in every direction. This is part of Newton's shell theorem, and Newton proved it a bit more rigorously using ellipses, but that's the basic idea. This is why if you are inside a hollow sphere, the field is going to be zero. And it works, of course, equally well if you're inside a charged sphere and you're trying to work out as long as it's uniformly charged, and you're trying to work out the field strength. So if you're inside a conducting sphere, the electrical field is zero, and if you're inside a sphere of mass, then the gravitational field due to that is zero. So that's why you don't have to worry about this piece of the Earth. You don't have to worry about this piece of the Earth which is above you. You only have to worry about the green shaded bit of the Earth which is beneath you. That's the only bit of the Earth that you have to worry about its field strength. So, what is the field strength? Well, the field strength is going to equal G minus Gm over little r squared. But this is going to be the mass of cut down sphere. So how big is that? Well, m is going to equal the total mass of the Earth multiplied by the ratio of the little r to big R cubed, because we've got a sphere whose volume is 4/3 pi r cubed divided by 4/3 pi r cubed. Of course, the 4/3 pi cancels, so m is going to equal the mass of the Earth multiplied by r cubed over big R cubed. So what we're going to have then, therefore your G is going to equal minus G times the mass of the Earth divided by, multiplied by R cubed over big R cubed divided by little r squared. So we're going to get minus Gm of the Earth divided by big R cubed multiplied by R. Oh, look. G is proportional to R. So what we're going to find, if we were to plot G versus R, little r like that, and let's say that is big R, the radius of the Earth, that thing there is little g, and basically it's going to be zero right in the middle, and then as we go out to, it's going to reach a maximum there, and we're going to be increasing linearly up until we get out to the surface, and then it begins to fall. So if we go twice as far away to kind of 2r, it'll be a quarter as big, it'll be about there, so we're going to get an inverse square going out from there, something like that. Yeah, it'll basically be like that.